Hi, I'm Alan, and today I'll be talking about model stealing for any low-rank language model. This is joint work with Ankur Moitra. So let me begin with some motivation. So nowadays we have API access to these trained large language models like ChatGPT. I can go online and I can query ChatGPT, I can ask it some questions. But is providing this API access actually secure? These large language models cost millions and millions of dollars to train, and their inner workings, like their parameters and even their hyperparameters, are generally kept a closely guarded secret. But what can an attacker actually learn through trying to exploit this API access? This is precisely the question that model stealing seeks to address. So model stealing is the question of, given query access to a machine learning model, can we recover the model or parts of the model? For a large language model, this would mean we would make a bunch of text queries and then try to learn something from the responses to those queries. And so this example shown on the slide here is actually a real example for the language model DeepSeek v3 that is an earlier version of the DeepSeek model that has been all over the news in the past few months. And so this model has the interesting quirk in its behavior that when you ask it, what model are you? Depending on how you ask the question, sometimes it will correctly say, I'm DeepSeek v3, and other times it will erroneously think that it is ChatGPT. And perhaps this says something about the data that the model was trained on. And in fact, this DeepSeek model was at the center of some recent controversy, with OpenAI claiming that DeepSeek may have inappropriately used its data and inappropriately used this query access to GPT. And so model stealing is an important problem in machine learning, and there have been many empirical works on model stealing over the past few years. And so one example that's perhaps most relevant to what I'll talk about today is this 2024 paper by Carlini et al. Titled Stealing Part of a Production Language Model, where the authors actually show how to provably steal parts of, namely the embedding dimension and sort of the last projection layer of real production language models. But our main focus in this talk today will be on developing theoretical foundations for understanding what models can be stolen. So despite the extensive empirical work on model stealing, so far we have a very limited theoretical understanding of model stealing. And yet addressing this question is important for understanding the feasibility of certain models in big tech. So certainly understanding theoretical foundations and the power and limitations of what models can be stolen will have a big impact on the industry. And so specifically today, I'll focus on the following question. So are there algorithms with provable guarantees for stealing some interesting family of language models? And here is an outline of what I'll talk about today. So let me begin with the basic theoretical setup. So okay, we consider a finite space of tokens, Z. So think of Z as, say, the space of all possible words. And we consider a fixed sequence length, T. Now we have this very literal definition of a language model, which is just a distribution D over sequences of words of length exactly T. So for simplicity, we have this fixed sequence length T. So next, we formalize the way in which the learner may query the language model. So the learner may make what we call conditional queries. And so in a conditional query, the learner specifies some prefix h of length, say, little t, and then they receive a sample f drawn from the posterior distribution conditioned on the prefix h. And so this is like the way you would interact with a real language model. You have some query h, and then you get some response f. And so now the question of model stealing specifically will be understanding under what structural assumptions on this distribution D, so structural assumptions on the language model, can we efficiently steal the language model via conditional queries? And by stealing the language model, I mean really just learning this distribution D. So to motivate what structural assumptions are natural for thinking about here, it will be instructive to go back and consider what is, in some sense, the original language model. So HMM, so hidden Markov models, are in many ways the original language model used in many of the earliest natural language processing systems, such as the IBM speech alignment models in the 1970s. And so quickly, mathematically, an HMM is defined as follows. There is a hidden state space S, and at each state S, there is some, say, observation distribution over the alphabet output space Z. And then there is a Markov chain over the hidden state space. And then at each time step, you get an observation Z sub t that is sampled based only on the hidden state S sub t at that time step. Okay. So the key structural property about HMMs is that they're low rank. And they're low rank in the following sense. So for every possible prefix length at t, we can construct the following matrix M sub t, the following very large exponentially large matrix. And so its rows are indexed by all possible histories H, and its columns are indexed by all possible futures F. And its entries are given by the conditional probability of each future conditioned on each history. And so the main structural property is the following. So if the distribution D is generated by an HMM with, say, S hidden states, then this matrix M has rank at most S for all possible prefix lengths t. And to see why this is true, the intuition is the following. Basically, the history H determines a posterior distribution over the space of hidden states S, which then exactly determines the distribution of the future F. And so we can basically factorize over this posterior distribution on the hidden states. And so this motivates the definition of a low rank distribution. And so we say a distribution D over sequences of words has rank S if for all possible prefix lengths t, the history by future matrix MT constructed on the previous slide has rank at most S. And so by what we just showed, we know that low rank distributions include HMMs, but they also include various generalizations like mixtures of HMMs or time varying HMMs and various others. And so now we can ask more concretely, can rank be a useful structural property for understanding model stealing? In particular, can we hope to steal any low rank distribution? So this question ties into some maybe more well-studied classical lines of work in algorithms and learning theory. So there's been a lot of previous work on learning HMMs from passive samples. However, the bottom line is that learning from passive samples is computationally hard in general because HMMs can encode, say, hard problems like noisy parodies. So this then motivates the question of whether we can sort of circumvent these computational barriers through active queries. And so this ties into the broader theme of understanding computational separations between active and passive learning. And in fact, one of the earliest examples of this paradigm was Angluin's L-star algorithm for learning deterministic finite automata from membership queries. And the question of learning HMMs can be seen as a statistical generalization of Angluin's sort of L-star algorithm for learning finite automata. Perhaps most directly relevant to what I will discuss today is this recent work of Kakde Krishnamurthy, Mahajan, and Zhang in 2023 that studies exactly this problem of learning HMMs via conditional queries. But the bottom line is that their, their result requires this additional assumption of high fidelity, which holds only in limited settings. And moreover, this assumption of fidelity is both hard to interpret and hard to justify. And thus, the question of whether learning with no additional assumptions is possible remains open. So our main result is exactly this. So we show that for any low rank distribution D over sequences of words, so if it has rank at most S, then we can, in polynomial in all relevant parameters, using a polynomial number of conditional queries and runtime, we can learn a distribution D prime that is efficiently sampleable and epsilon close in TV distance to the original distribution. So this gives, in some sense, the first provable model stealing algorithm in a natural setting for language. And it's also nice that our algorithm has some natural built-in robustness, that it works even if this distribution D, the original distribution, is not exactly low rank, but merely close in TV distance to a low rank distribution. All right, so next, let me try to give a little bit of insight into the algorithmic and sort of technical tools in our results. So the first important question about a low rank distribution is, how can we even efficiently represent a low rank distribution? Recall that low rank is defined in terms of these exponentially large history by future matrices. And so how can we even construct a succinct, polynomially sized representation? So the main challenge here is that there are actually exponentially many possible histories, so exponentially many rows of this matrix. So how can we represent histories that we have never seen before or we don't have room to store? So the main insight is the following. We can, for each history h, we associate the vector v sub h to be the row vector indexed by the history h of this above matrix. So this vector v sub h is an exponentially long vector, but now we will think of histories as their associated vectors, and we can now do linear combinations between different histories. And so in particular, because this matrix M has rank at most S, we can store a spanning set of rows H1 through HS, and then all other histories can be written as a linear combination of the elements of this spanning set. And so throughout this talk, we'll use histories and their associated vectors interchangeably. And even though these vectors are exponentially long, we'll never actually need to write out these full vectors. And instead, we'll only just store the names of the histories that index these corresponding vectors. So beyond any spanning set, it will be useful to store a well-behaved spanning set. And so fortunately, we have this classical notion of a barycentric spanner. So given a collection of vectors, a subset of them is a barycentric spanner for the full collection. If any element of the collection can be written not just as a linear combination, but a linear combination with bounded coefficients of the elements of the barycentric spanner. And so these bounded coefficients are precisely why barycentric spanners are useful for algorithms. And so fortunately, we have this classical fact that any collection of that barycentric spanners always exist. So for a collection of vectors in, say, an S-dimensional subspace, there is a subset of size S that forms a barycentric spanner. And thus, instead of any spanning set, we can actually store a barycentric spanner. Okay, so now I can go back to the problem of representing this low rank distribution. So the first piece of this representation will be for each possible prefix length little t, we'll store a subset ht that is a barycentric spanner for the set of all possible histories of length little t. But we'll also need to store a few additional details. Namely, we'll need to store transitions between these different barycentric spanners. And so first, we'll store the next token probabilities for all of the histories h in ht. And then we'll also store a change of basis matrix, specifically to write all of the elements of ht concatenated with any possible next token z as a linear combination, so in terms of the elements of ht plus 1. So this change of basis matrix basically lets us rewrite elements of ht concatenated with some arbitrary token in terms of the elements of ht plus 1. And so now, in order to demonstrate that the elements above give me a complete representation, I need to show how to draw samples given this representation. And so given this representation, we can draw samples as follows. So we sample one token at a time. And so we always maintain our current string as a linear combination of the elements of the corresponding barycentric spanner, say ht. And then we sample the next token, say z sub t plus 1, and we sample this token with probabilities as prescribed by basically the linear combination and the stored next token probabilities. And then once we've sampled this next token, we basically use this change of basis matrix to rewrite this new string, now x concatenated with z sub t plus 1, in terms of the elements of ht plus 1, the t plus first barycentric spanner. And after doing this change of basis operation, we can then induct and sample the next token and kind of repeat the process. Okay. Okay, so this completes the first step of understanding how to represent a low rank distribution. Of course, there are still many additional challenges. And so perhaps the most obvious one is that we actually need to learn this representation. And so I'll actually skip this part for the talk today. However, there's a second important challenge that I will focus on. And so let's pretend that we've already learned some representation of the previous form. But crucially, learning is always only, say, epsilon approximate. So say we've learned an approximate representation of the previous form. But now the crucial challenge is that the previous argument for sampling actually really needs an exact representation. But what happens when you only have an approximate representation with errors? So it turns out that controlling the potential compounding or blowup of the errors is a significant challenge and will require some new conceptual ideas. So specifically, what goes wrong? So recall that in the sampling algorithm, we maintain our current string x as a linear combination of the elements of ht. But now the problem is that the estimated coefficients in the linear combination may grow exponentially over time, causing errors to be amplified exponentially. So let me point out here that even though ht is a barycentric spanner, so a good, say, bounded coefficient linear combination exists, because ht can be sort of arbitrarily poorly conditioned, if we do our change of basis operations naively, we may get worse and worse conditioned linear combinations. So the linear combination that we estimate could still have coefficients that are blowing up exponentially over time. Yeah. So to resolve this question, it turns out that it suffices to solve a pretty clean abstracted geometric problem. So I won't be able to say exactly how this problem arises, but it does have a nice, clean conceptual takeaway. So the sort of abstracted problem that we'll need to solve is the following kind of projection problem. And the problem is as follows. So let delta D be the simplex in RT. Now we have a point, our estimate in the simplex. So this is in some sense corresponds to our estimated linear combination. There's a convex set K that's a subset of the simplex. And so K kind of corresponds to the bounded coefficient subset that we want to project onto. And then there is some unknown target point V star in K that kind of corresponds to the ground truth good linear combination. Now, the projection we want to do is we want to replace our estimate with a point V prime in K while ensuring that we decrease the distance to the ground truth V star. Now, I haven't said what the right notion of distance is yet, and this will be the key. So recall that these points are in the simplex, so they really correspond to probability distributions. And our end goal is to learn some distribution to some like accuracy and TV distance. And so therefore, our measure of distance must be compatible with sort of our end goal of learning in TV distance. So this motivates perhaps the first natural attempt, which is to measure distance as TV distance. So TV distance is the same as L1, and so the guarantee we need, so since we don't know V star, we basically need to choose V prime so that for all points V star in K, V prime is closer to V star than our original estimate. Okay? But unfortunately, L1 as a metric is such that it is impossible to satisfy the above for all V stars simultaneously. And so roughly, like the intuition is that L1 is such that basically different choices for V star require different projection points V prime. And so solving this problem where the distance is measured with respect to L1 is actually impossible. The main insight is that even though our end goal is to learn in TV distance, we can use a different measure of distance as a proxy for tracking the error throughout all of the intermediate steps. And in particular, we can use KL divergence as a proxy for TV distance. And so crucially, KL divergence has the following property. So KL divergence has the property that when I project onto a convex set in KL, so when I let V prime be the projection in KL, then I actually decrease the KL divergence to all points in my convex set K. And so this is exactly the property that failed for L1 on the previous slide, but it holds for KL. So thus, to solve this kind of clean abstracted problem, we want to project in KL divergence. And so this will ensure that we always decrease the distance to V star, at least when measured using KL. And so briefly, jumping back up a level, going back to the overall sampling algorithm. So recall the original sampling algorithm is sample token by token, sort of iterate these change of basis operations. But it turns out that to deal with or prevent the compounding of errors, it requires a third step, which is after each change of basis operation, you basically solve some projection in KL to ensure that the coefficients in your estimated linear combination remain bounded. So this brings up an interesting conceptual point, which is that while the kind of idealized sampling algorithm is fully linear, this third step with a nonlinearity seems crucial for controlling the compounding of the errors. And perhaps taken even more broadly, this is an interesting theoretical example where essentially allowing for this more complex test time or inference time computation, namely this projection in KL, seems to improve stability over long time horizons. Okay. Finally, let me very briefly comment on the connection between our theory and modern language models. Okay. So in light of the theory, perhaps the most natural question we want to ask is there any sense in which modern language models are low rank? And so let me explain our experimental setup. So for n is say 4,000, we sample a bunch of histories from the language model. And also for each history, let's sample one future condition on this history. So this gives us n futures and n history, sorry, n histories and n futures, and say there are 16 tokens, or roughly 16 words each. And now we construct the following matrix, whose rows are indexed by the histories and columns are indexed by the futures. And it turns out that instead of the conditional probabilities, it will be useful to have the log probabilities instead. And so what we find is actually that this log probability matrix is shockingly low rank for like maybe relatively small scale, but still like modern language models like Gemma and small versions of Llama. And in fact, there's this kind of consistent power law decay in the singular values for this kind of history by future matrix. And so while our theory was for a slightly different matrix, like this matrix of conditional probabilities, it seems that taking the log actually results in a like low rank structure for modern language models. And I think there are some quite interesting open questions for whether we can sort of extend our theory for low rank language models to these kind of log low rank language models. And I'm happy to talk more about this offline. And I'll conclude there. Thank you.